the event horizon, time itself begins to stretch like honey falling from a spoon, slow, golden, impossible to rush, and what feels like minutes to the one falling might be centuries to anyone watching from far away. There is something strangely peaceful about this truth, about the way physics bends toward the unknowable, about how the universe holds spaces where all the familiar rules grow soft and dissolve. If these quiet journeys through strange and beautiful ideas help carry you toward rest, a subscription means more of them will find their way to you in the nights ahead. The fall into a black hole is not violent, not at first, not in the way one might imagine. It is gradual, almost meditative, a slow surrender to gravity's deepest patience. The stars behind begin to blur and shift, light curving around the darkness ahead. And here, at the edge of everything known, the descent begins. In the year 1971, a satellite called Uhuru was drifting through the quiet darkness above the Earth, its instruments trained on the heavens, listening for whispers in a language that human eyes could never detect. Uhuru, which takes its name from the Swahili word for freedom, had been launched from a platform off the coast of Kenya on the 7th anniversary of that nation's independence, and now it circled our planet with patient purpose, cataloguing the X-ray sources that pepper the sky like distant campfires glimpsed through fog. Among its discoveries was an object in the constellation Cygnus, designated Cygnus X1, which appeared to be locked in an orbital dance with a blue supergiant star some 6,000 light-years from where you are lying now. The X-rays streaming from this region told a peculiar story, one of matter being pulled from the visible star and spiraling downward into something that could not be seen, something so dense and so gravitationally powerful that it heated the infalling gas to temperatures of millions of degrees before swallowing it entirely. This was the first strong observational evidence for what physicists had been contemplating in their equations for decades: an object so collapsed that not even light could climb out of its gravitational well, an object that would come to be known, in the common parlance, as a black hole. The term itself had been given its modern astronomical meaning just a few years earlier, in 1967, when the physicist John Wheeler used it during a lecture at a NASA conference, finding in those two simple words a poetry that the previous technical descriptions had lacked. Before Wheeler's memorable phrasing caught on, these objects had been called frozen stars, or dark stars, or simply gravitationally collapsed objects, which, while accurate, did not capture the imagination quite so readily. Wheeler himself later said that he had adopted the term after hearing it suggested by someone in the audience, though the exact origins remain somewhat hazy, as origins often do, with earlier uses appearing here and there in print. But it was Wheeler's repeated use of the phrase, and his considerable influence in the physics community, that cemented black hole as the name by which we would all come to know these strangest of cosmic objects. And there is something fitting in the fact that a concept so difficult to visualize was given a name so simple and so evocative that even a child can picture it. A hole in the fabric of everything, black as the deepest sleep. The mathematical groundwork for these objects had been laid much earlier, in circumstances that seem almost impossibly poignant when you consider them. In 1916, while serving as an artillery lieutenant in the German army on the Russian front during the First World War, a physicist named Karl Schwarzschild found time between the chaos of conflict to work through the implications of Albert Einstein's newly published general theory of relativity. Einstein had presented his field equations just weeks before, describing how mass and energy curve the geometry of space-time itself. And Schwarzschild, despite the mud and cold and uncertainty of war, set about finding an exact solution to those equations for the simplest possible case: a perfectly spherical, non-rotating mass. What he discovered was remarkable, and the solution he sent to Einstein from the front lines contained within it an ominous feature, a radius at which the mathematics behaved very strangely indeed, a boundary where the curvature of spacetime became so severe that the equations seemed to fold in on themselves. This came to be called the Schwarzschild radius, and for any given mass, you can calculate its value with a formula of elegant simplicity, where you take twice the mass, multiply it by the gravitational constant, and divide by the speed of light squared. If you were to compress our own Sun, with all its blazing fury and its diameter of nearly 1.5 million kilometers, down to its Schwarzschild radius, you would end up with a sphere just 3 kilometers across, about the distance you might walk in half an hour on a pleasant afternoon, and yet containing all the mass that currently lights our days and warms our faces. Schwarzschild himself did not live to see his solution become the foundation for black hole physics, as he died just months after sending his calculations to Einstein, succumbing to an autoimmune disease contracted during his service. But his name lives on in every discussion of these objects, a quiet memorial to a mind that found clarity even amid the senselessness of war. For many years, the Schwarzschild solution was regarded as a mathematical curiosity rather than a description of anything that might actually exist in the universe. Einstein himself was skeptical that nature would ever produce such extreme conditions, and he published a paper in 1939 arguing that matter could not be compressed past a certain point, that some physical process would always intervene to prevent the formation of what we would now call an event horizon. The event horizon, you see, is the name given to that spherical boundary at the Schwarzschild radius, the surface beyond which events can no longer communicate with the outside universe, the point of no return past which even light, traveling at 300,000 kilometers per second, finds itself running up a slope too steep to climb. It is not a physical surface in the way that the crust of a planet is a surface, not something you could touch or stand upon, but rather a geometric feature of spacetime itself, a one-way door that swings only inward, or perhaps more accurately, a region where all possible paths through the fabric of reality point in the same direction, toward the center, toward the singularity, toward an end that we do not yet fully understand. The mathematics that describe the event horizon are well established, but what truly happens to matter and information that cross it remains one of the most profound puzzles in modern physics. A puzzle that has kept some of the finest minds occupied for generations and shows no sign of yielding its secrets easily. Physics has a long and honorable tradition of thought experiments, those carefully constructed imaginary scenarios that allow us to probe the implications of our theories without the expense and practical difficulties of building actual apparatus. Einstein was particularly fond of them, and his most famous was perhaps the elevator thought experiment, in which he imagined a person standing in an enclosed box, unable to see outside, and asked whether that person could distinguish between being accelerated upward through empty space and standing still in a gravitational field. The answer, Einstein proposed, was no, that the two situations would feel identical from the inside, and this simple insight became one of the cornerstones of general relativity, the principle of equivalence that connects acceleration with gravity in a way that Newton's physics never could. Erwin Schrödinger contributed his own memorable thought experiment, that of a cat in a box whose fate is linked to a quantum event. And while the scenario was intended to highlight what Schrödinger saw as an absurdity in the Copenhagen interpretation of quantum mechanics, it has instead become a touchstone for discussions of superposition and measurement and the strange behavior of the very small. Now we come to another thought experiment, one that has occupied physicists and science communicators alike. The question of what you would actually experience if you were to fall into a black hole, not as a probe or a particle but as a conscious observer, a person with a heartbeat and memories and a sense of self, drifting toward an event horizon with nothing but time and curiosity. In April of 2019, the Event Horizon Telescope collaboration released an image that had required the coordinated efforts of radio telescopes spanning the globe, from Antarctica to Hawaii to the mountains of Spain, all linked together to form a virtual dish the size of the Earth itself. The target of this extraordinary endeavor was a supermassive black hole at the heart of the galaxy Messier 87, some 55 million light-years from our own small world, a distance so vast that the light captured in that image began its journey when our ancestors were not yet quite human, when multiple species of early hominids still walked the African continent. The black hole itself contains approximately 6.5 billion times the mass of our Sun, a number that resists easy comprehension, and the image revealed a glowing ring of superheated gas surrounding a dark central shadow, the silhouette of the event horizon against the bright background of its own accretion disk. That image, blurry though it appeared to some eyes, represented one of the great triumphs of human curiosity and cooperation, a direct glimpse of something that had been purely theoretical for over a century, and it confirmed that the mathematics of Schwarzschild and Einstein and all who followed describe something real, something out there in the darkness between the stars, waiting with infinite patience. For our thought experiment, we shall choose a supermassive black hole rather than a stellar mass one, and this choice is important for reasons that will become clear as we proceed. A stellar mass black hole, the kind formed when a massive star exhausts its fuel and collapses, typically contains between 3 and perhaps 20 times the mass of our Sun, compressed into a region of such small radius that the gravitational gradients near its event horizon are extraordinarily severe. The difference in gravitational pull between your feet and your head, if you were falling feet first toward such an object, would be powerful enough to stretch you like warm toffee long before you reached the horizon itself, a process that physicists have given the rather whimsical name of spaghettification. But a supermassive black hole, of the kind we have just been discussing, has an event horizon so much larger, despite its greater mass, that the gravitational tides at the boundary are actually quite gentle, at least by the extreme standards we are dealing with here. You could cross the event horizon of a black hole containing billions of solar masses and notice nothing amiss, at least not immediately. At least not until much later when the tides begin to build and the interior reveals its nature. And so we shall imagine that you are an astronaut, perhaps far in the future when such journeys are possible, drifting in a small vessel toward a supermassive black hole in the center of some distant galaxy, chosen specifically because it will allow you to experience the crossing of the threshold without immediate destruction. The scene, then, is set. You are alone in your spacecraft, though not lonely, merely quiet, floating in the deep calm that spaceflight encourages, watching through your viewscreen as the black hole grows slowly larger against the background stars. Those background stars are beginning to behave strangely, their light bent by the intense gravitational field into patterns that no earthly sky has ever shown. And the hole itself is not truly black but ringed with fire, the glow of matter spiraling inward at velocities that approach a significant fraction of the speed of light. You have plenty of time, hours or days depending on your approach trajectory, and you spend that time simply watching, simply breathing, simply being present for something that no human being has ever witnessed. What happens next will be explored in the sections that follow, but for now, it is enough to know that you are there, at the edge of forever, where the mathematics becomes music and the questions become experiences, where everything we have learned about gravity and light and time comes together in a single extraordinary moment. The universe has been building toward this instant for 13.8 billion years. And you are present. And that presence is perhaps the most remarkable thing of all, though we shall discuss it calmly, and slowly, and with all the patience that the subject deserves. Let us begin now with the long approach, the slow and patient journey inward from a distance that still seems almost safe, though of course it is not. Not really, for you have already committed yourself to this particular trajectory, and there is a certain inevitability to what follows, though it will unfold so gradually that you might almost forget, for a time, that you are falling at all. From several million kilometers away, the black hole does not appear as you might expect, which is to say it does not appear as a hole in any conventional sense. Not as a dark circle punched cleanly from the fabric of space, but rather as a distortion, a peculiar wrongness in the arrangement of the stars, a place where the familiar patterns of the night sky have become somehow confused, as though someone had taken a small region of the cosmos and gently stirred it with an invisible spoon. The stars near the center of your view seem to have drifted from their proper positions, and some of them appear to be in places where you are quite certain they should not be, and others seem to have multiplied, appearing twice or even several times in an arc that curves around the central darkness in a way that defies your intuition about how light ought to behave. This phenomenon, which we call gravitational lensing, was one of the earliest and most elegant predictions to emerge from Albert Einstein's general theory of relativity, which he completed in November of 1915 after nearly a decade of concentrated thought on the nature of gravity and the geometry of spacetime. In that theory, Einstein proposed that massive objects do not simply pull on other objects through some mysterious action at a distance, as Newton had supposed, but rather that they curve the very fabric of spacetime itself, and that objects moving through this curved spacetime follow paths that appear to us as the effects of gravitational attraction. Light, too, must follow these curved paths, for light has no choice but to travel along the contours of the spacetime through which it moves, and so a beam of light passing near a massive object will bend, curving gently toward the mass before continuing on its way. Einstein calculated that starlight passing close to the edge of our own sun should be deflected by approximately 1.75 arcseconds, which is a very small angle indeed, roughly equivalent to the apparent width of a human hair viewed from 10 meters away, and yet it was an angle large enough to be measured with the astronomical instruments of the early 20th century, provided one could observe stars very close to the sun's edge, which of course is normally impossible because the sun's brilliance overwhelms everything nearby. The solution, Einstein realized, was to wait for a total solar eclipse, when the moon would block the sun's blinding light and the stars near its edge would become briefly visible against the darkened sky. The opportunity came in May of 1919, when a total solar eclipse would be visible from a narrow band crossing the Atlantic Ocean and passing over parts of South America and West Africa. The British astronomer Arthur Stanley Eddington, who had become one of the few scientists outside of Germany to fully appreciate Einstein's new theory, organized 2 expeditions to observe the eclipse and measure the positions of stars near the sun's edge. One team traveled to Sobral in northern Brazil, while Eddington himself led the second expedition to the island of Principe, a small volcanic island off the west coast of Africa, in what was then Portuguese West Africa. The journey was not easy, and the equipment was heavy and delicate, and when the day of the eclipse arrived, Eddington faced the astronomer's eternal enemy, which is cloud cover, and for much of the crucial minutes of totality the sky was obscured, though it cleared just enough, just in time, for a few precious photographs to be taken. When the photographic plates were carefully measured and the calculations completed, the results showed that the stars near the Sun had indeed shifted their apparent positions by an amount that matched Einstein's prediction rather than the smaller deflection that Newton's theory would have suggested. And this confirmation, announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London in November of 1919, made Einstein famous virtually overnight, transforming him from a respected physicist known mainly to specialists into a global celebrity whose name would become synonymous with genius itself. Now, as you drift closer to the black hole, you are witnessing gravitational lensing on a scale that would have astonished Eddington and Einstein alike. For the mass concentrated before you is not merely that of a star but millions or even billions of times greater, and the curvature of spacetime is correspondingly more extreme. The distant stars are no longer simply shifted slightly from their true positions but are being dramatically distorted, their light bent through such severe angles that multiple images of the same star can appear simultaneously, arranged in arcs and rings around the central darkness. If you were to focus your attention on a single star that lies directly behind the black hole, precisely along your line of sight, you would see something quite remarkable, for the light from that star would be bent around the black hole not just on one side but on all sides simultaneously, creating a perfect ring of light encircling the dark center. A phenomenon that we call an Einstein ring in honor of the man who first understood why such a thing must occur. More commonly, when the alignment is not quite perfect, you will see the star's light stretched into arcs or appearing as multiple distinct points, distorted copies of the same object created by light that has taken different paths around the gravitational lens. As you continue your slow approach, falling ever deeper into the curved spacetime, you will notice that the dark region at the center of your view begins to take on a more distinct character. It is not simply an absence of light but rather a region bounded by a faint and ethereal glow, a thin ring of brightness that seems to hover at the edge of the darkness, and this ring marks the location of what we call the photon sphere, which is perhaps the strangest boundary you will cross before reaching the event horizon itself. The photon sphere exists at a distance of exactly 1½ Schwarzschild radii from the center of the black hole, where the Schwarzschild radius is the characteristic size of the event horizon for a non-rotating black hole of a given mass. At this particular distance, the curvature of spacetime is precisely sufficient that a photon, a particle of light, traveling in a direction tangent to the black hole will be bent into a circular orbit, neither falling inward nor escaping outward but instead circling the black hole indefinitely, or at least it would do so if the orbit were perfectly stable, which unfortunately it is not. The photon sphere is what physicists call an unstable equilibrium, meaning that any photon orbiting there will eventually either spiral inward toward the event horizon or escape outward to infinity, depending on the slightest perturbation. What you see as you look toward this region is light that has been captured into these unstable orbits, some of it circling the black hole once before escaping toward your eyes, some of it circling twice, some circling many times, each orbit creating a separate thin ring of light nested inside the previous one. The result is a series of concentric bright bands, each one thinner and fainter than the last, stacked together at the edge of the dark shadow. This phenomenon was not fully appreciated until quite recently in the history of astrophysics, and it was revealed in striking detail through the visual simulations created for the film Interstellar, which was released in 2014 and which featured some of the most accurate depictions of black holes ever produced for a popular audience. These simulations were developed under the guidance of the theoretical physicist Kip Thorne, who had spent decades studying the mathematics of black holes and gravitational waves, and who would later share the Nobel Prize in Physics for his role in the detection of gravitational waves in 2015. When Thorne and the visual effects team at Double Negative, led by Paul Franklin and Oliver James, began the painstaking work of calculating exactly what a black hole would look like to a nearby observer, they discovered features that had never been clearly visualized before, including these thin bright bands at the edge of the shadow, which Thorne termed the photon rings. The calculations required enormous computational resources, tracing millions of individual light rays through the curved spacetime and determining which rays would reach the hypothetical camera and from what direction they had originally come. The results were both beautiful and scientifically valuable, and several academic papers were published describing the new insights that emerged from this collaboration between physics and filmmaking. For a black hole of the size that lurks at the center of our own galaxy, the one we call Sagittarius A star, which contains approximately 4 million times the mass of our Sun and lies some 26,000 light-years from Earth, the photon sphere would be a region approximately 22 million kilometers across. This is a span roughly 15 times the diameter of our Sun, which seems quite large until you remember that you are speaking of an object containing the mass of 4 million suns, compressed into a region of spacetime so warped that light itself cannot help but fall inward once it crosses the event horizon. As you continue your descent, you may become aware of another presence in the space around you, a presence that does not derive from the black hole itself but from the matter that is falling inward alongside you, the great swirling river of gas and dust that we call the accretion disk. This material has been gathered from the surrounding environment over millions of years, drawn from nearby stars and interstellar clouds, and it does not fall directly into the black hole but instead settles into a flattened disk that spirals slowly inward, like water circling a drain. The accretion disk is not a calm or peaceful structure, for the material within it is moving at tremendous speeds, and the inner regions are moving faster than the outer regions, and this difference in speed creates friction between adjacent layers of gas, and this friction heats the gas to extraordinary temperatures, and this heat causes the gas to glow with an intensity that can outshine entire galaxies. In the innermost regions of the accretion disk, where the material approaches the event horizon, the temperatures may reach millions or even billions of degrees, and the radiation emitted is primarily in the form of X-rays, which are far beyond what human eyes can perceive. Though if your eyes were sensitive to such radiation, the disk would appear almost blindingly bright. The appearance of the accretion disk is further complicated by the extreme speed at which it rotates, for in the inner regions the gas is moving at a substantial fraction of the speed of light, and at such speeds the effects of special relativity become significant. One of these effects is called Doppler beaming, or sometimes relativistic beaming, and it causes the side of the disk that is moving toward you to appear dramatically brighter than the side that is moving away. The light from the approaching side is compressed and intensified by the motion, shifted toward higher frequencies and concentrated in your direction, while the light from the receding side is stretched and diminished, shifted toward lower frequencies and spread away from your line of sight. The result is that the accretion disk does not appear symmetric but rather lopsided, with one side blazing with light and the other side fading into dimness, and this asymmetry shifts as your own position changes relative to the disk, always keeping the brighter side on the edge where the material is rushing toward you. Combined with the gravitational lensing, which causes the far side of the disk to appear bent upward and visible above the black hole's shadow, the total effect is one of surpassing strangeness, a glowing structure that seems to wrap around the darkness in ways that defy ordinary intuition. And so you fall, slowly, gently, watching the stars multiply and dance around the growing shadow, watching the photon rings shimmer at the edge of darkness, watching the accretion disk blaze and twist in its endless spiral. And all of this unfolds with a patient inevitability, for there is no hurry here. Not yet. And the black hole will wait for you, as it has waited for billions of years. And there is nothing to do now but watch, and fall, and perhaps to sleep. Let us turn now to something rather beautiful, which is the way time itself begins to change its character as you drift closer to a black hole. This is not a metaphor or a poetic flourish but actual physics, worked out with great care by Albert Einstein in his general theory of relativity, which he completed in 1915 after nearly a decade of what must have been extraordinarily demanding mathematical labor. What Einstein showed, among many other things, was that time does not flow at the same rate everywhere in the universe. It runs slower in regions where gravity is strong and faster in regions where gravity is weak. And this difference is not merely apparent but deeply real, woven into the fabric of space-time itself. To understand why this matters for your gentle descent toward a black hole, we should first consider how this phenomenon, known as gravitational time dilation, was actually measured here on Earth, in conditions far less exotic than anything involving collapsed stars. In 1960, two physicists at Harvard University named Robert Pound and Glenn Rebka performed a remarkably delicate experiment in the Jefferson Tower, which rises about 22.5 meters from its base to its top. They used gamma rays emitted by iron atoms, measuring whether these rays shifted very slightly in frequency as they traveled upward against Earth's modest gravitational pull. And they did shift, by an amount almost unimaginably small, about 2 parts in 10 to the 15th, which is to say 2 parts in 1,000 trillion. Yet this tiny shift was precisely what Einstein's theory predicted, confirming that even over the height of a university building, time runs at a fractionally different pace at the top than at the bottom. The clocks at roof level tick just slightly faster than the clocks in the basement, not because anything is wrong with the clocks, but because that is how time actually behaves when gravity is present. Now, you might wonder whether such minuscule effects have any practical consequences in daily life, and the answer is that they do, in ways that have become so routine we scarcely think about them. The satellites that comprise the Global Positioning System orbit Earth at an altitude of roughly 20,000 kilometers, where gravity is weaker than at the surface, and they travel at significant speed relative to the ground. Both of these factors affect the passage of time, and if the satellite clocks were not corrected for relativistic effects, they would drift by approximately 38 microseconds each day relative to clocks on the ground. This may sound trivially small, but because the system works by measuring the travel time of radio signals, and because those signals move at the speed of light, even microseconds matter. Without accounting for relativity, positional errors would accumulate at a rate of roughly 10 kilometers per day, which would rather quickly render the system useless for navigation. So every time you use a map application on your telephone to find your way somewhere, you are relying, in a quiet and unobtrusive way, on Einstein's insights about the nature of time. With this foundation in place, let us imagine what happens as you continue your peaceful fall toward the black hole we have been visiting together. As you descend into regions of ever stronger gravity, the rate at which your clock ticks, as measured by someone far away, begins to slow rather dramatically. This is not because anything strange is happening to you personally, not because you feel any different or notice any change in your heartbeat or breathing, but because the fabric of space-time itself is curved so steeply that time flows at a measurably different pace where you are compared to where a distant observer might be watching. And this brings us to one of the most peculiar aspects of falling into a black hole, which is the profound difference between what you experience and what someone watching from a great distance would see. From your perspective, as we shall explore more fully in a moment, the fall proceeds in a perfectly ordinary fashion. You drift inward. The stars will slowly overhead if you happen to be tumbling, and after a finite amount of time by your own clock, you cross the boundary known as the event horizon and continue falling toward whatever lies within. It is all rather undramatic, in a certain sense, at least until you approach much closer to the center. But for a distant observer, watching through a powerful telescope, something altogether different appears to happen. As you fall deeper into the gravitational well, the light reflecting off you or emitted by any lamp you might carry must climb upward against an increasingly steep gravitational gradient. In doing so, it loses energy, which means its wavelength stretches longer, shifting from whatever color it started as toward the red end of the spectrum and then beyond into infrared, where human eyes cannot follow. Your image does not merely redden, it also dims. Because the photons carrying news of your presence arrive at the distant observer's telescope less frequently as time dilation takes hold. And so the observer sees you falling more and more slowly, your movements becoming sluggish, your image fading, the light growing redder and dimmer, until at last you appear to freeze just above the event horizon, never quite crossing it, hanging there in a kind of eternal stillness like an insect preserved in amber, though the amber in this case is made of bent spacetime rather than fossilized resin. This is not an illusion, nor is it a mere artifact of observational limitations. It is actual physics, a genuine consequence of how information must travel upward through warped spacetime in order to reach an observer far away. The distant watcher is not being deceived. They are simply receiving information that has been profoundly altered by its journey. In principle, if they waited long enough and had sensitive enough instruments, they could continue to receive ever redder, ever fainter signals from you for an extraordinarily long time, though in practice the light would become so dim and so shifted that no real instrument could detect it after a relatively brief period. This appearance of objects seeming to freeze at the horizon gave rise to an earlier name for these gravitational objects, one that was used particularly by Soviet physicists in the decades before the term black hole became widely adopted. They called them frozen stars, which captures rather nicely the way a collapsing star would appear to an outside observer, seeming to halt its collapse just as it reached its own critical radius, frozen in time from that external perspective even though the matter itself has long since fallen through and continued its journey inward. The name black hole was popularized in the 1960s, often attributed to the physicist John Wheeler, though its precise origin is somewhat murky, and it eventually displaced frozen star as the standard terminology. But frozen star is perhaps more evocative of what a distant observer actually perceives: that strange, asymptotic slowing that never quite reaches completion. In 1965, the mathematician and physicist Roger Penrose published a theorem that helped establish black holes as serious objects of study rather than mere mathematical curiosities. Working with new techniques involving what are called trapped surfaces, Penrose demonstrated that once matter collapses past a certain point, the formation of a singularity, a point of infinite density and curvature, becomes essentially inevitable according to general relativity. This was important because it showed that singularities were not merely artifacts of overly symmetric idealizations, but rather generic features that would arise from realistic gravitational collapse. Penrose's singularity theorem, along with subsequent work by Stephen Hawking and others, helped transform black hole physics from a somewhat speculative backwater into a central area of theoretical research. For this and related contributions, Penrose was awarded a share of the Nobel Prize in Physics in 2020, more than half a century after his original paper, which gives some indication of how long it can take for the significance of fundamental theoretical work to be fully recognized. Now let us return to your experience as the person actually falling. From your point of view, none of the dramatic freezing and reddening occurs. You do not perceive yourself as slowing down. You do not see the universe around you speed up in some bizarre fashion. You simply continue falling at whatever pace you were falling before. When you cross the event horizon, there is no sign, no marker, no sudden change in the quality of space or time. If you were not paying very careful attention to your instruments, you might not even notice the moment of crossing. The horizon is not a physical surface, not a membrane you push through or a barrier you break, but rather a mathematical boundary defined by the inability of light to escape. Inside that boundary, your future inevitably leads toward the center of the black hole, but at the moment of crossing, nothing special happens to your local experience. This is sometimes called the no-drama scenario, a reassuringly bland phrase for a reassuringly bland crossing. The drama, such as it is, comes later. This peaceful view of horizon crossing has been the standard picture in general relativity for many decades. But in 2012, a group of theoretical physicists named Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully published a paper that raised some troubling questions. Their argument, which became known as the AMPS paradox after their initials, concerned the relationship between general relativity and quantum mechanics, particularly the quantum mechanical properties of black hole radiation discovered by Stephen Hawking in the 1970s. Without going into the technical details, which are formidable, the AMPS argument suggested that the principles of quantum mechanics might be inconsistent with the no-drama scenario. Instead, they proposed that an infalling observer might encounter what they called a firewall at the event horizon, a violent burst of high-energy radiation that would be rather less pleasant than the gentle crossing Einstein's theory seemed to promise. The firewall proposal remains highly controversial, and many physicists have offered counterarguments or alternative resolutions to the paradox. It is fair to say that the question is not yet settled, and it touches on deep issues about how gravity and quantum mechanics fit together, questions that will likely require a full theory of quantum gravity to answer properly. For the purposes of our relaxing journey, we shall continue to assume the no-drama scenario, partly because it aligns with classical general relativity and partly because it is simply more soothing to contemplate a peaceful horizon crossing than a sudden incineration. But it is worth knowing that the physics community continues to debate what actually happens at this enigmatic boundary. What we can say with some confidence is that time, near a black hole, behaves in ways that are utterly unlike our everyday experience and yet are described with beautiful precision by equations that have been tested and confirmed in laboratories, in orbits around Earth, and in observations of distant stars and gravitational waves. Time flows at different rates in different places, runs slower where gravity is strong, and creates apparent paradoxes when viewed from different perspectives. And yet there is no real paradox, Only the gradual revelation that time is not the fixed and absolute river that Isaac Newton imagined, flowing ever onward at the same pace throughout the cosmos. Instead, it is something more fluid and strange, a river whose current varies from place to place, running swift and deep in some regions, slow and still in others. As you fall toward the black hole, you carry your own time with you, your own heartbeat, your own breath, your own thoughts unfolding at their accustomed pace. From your perspective, everything is normal. But to those you have left behind, you have entered a region of space-time so different from their own that they can never truly follow. Only watch your image fade and redden until it vanishes beyond the reach of any telescope. This is where time becomes something other than what we thought it was. Something shaped by matter and energy, by the geometry of the cosmos itself. It is strange and beautiful and, in its own quiet way, rather restful to consider. The notion that time is not a tyrant but merely a feature of the landscape, varying gently from place to place like the slope of a hill or the depth of a stream. And so we come now to the threshold itself, that curious boundary which separates the ordinary universe from whatever lies within. And I want you to understand something rather important about this boundary, something which took physicists many decades to properly appreciate, which is that the event horizon is not a thing at all, not in any physical sense that you might ordinarily recognize, but rather a mathematical abstraction, a surface defined purely by geometry and causality, marking the precise location beyond which light itself cannot escape to reach distant observers. And this distinction matters because you might naturally imagine crossing some kind of barrier, perhaps a shimmering membrane or a wall of energy or some detectable transition. But in truth there is nothing there to see, nothing to touch, nothing your instruments could measure at that exact moment of crossing. And this realization was not immediately obvious to the physicists who first studied these objects, because the mathematics of general relativity, when expressed in certain coordinate systems, seemed to suggest that something catastrophic happened at the horizon, that time stopped or space became singular, and this confusion persisted for several decades until a young physicist named David Finkelstein published a paper in 1958. A rather elegant little paper really, in which he demonstrated that the apparent singularity at the horizon was merely an artifact of the coordinate system being used. Much like how a map projection might make Greenland appear larger than Africa when in reality it is not. And Finkelstein showed that if you chose different coordinates adapted to an infalling observer rather than a distant stationary one, the mathematics became perfectly smooth and continuous at the horizon, revealing it to be what he called a one-way membrane, a surface which allows things to pass inward but never outward. And this was a crucial conceptual breakthrough because it meant that crossing the horizon is, from your local perspective, an entirely unremarkable event, that you would float through this invisible threshold feeling nothing unusual whatsoever. Which brings us to one of the most beautiful and counterintuitive principles in all of physics, the principle of equivalence, which Einstein placed at the very heart of his general theory of relativity, tells us that a freely falling observer in a gravitational field is locally equivalent to an observer floating in empty space, far from any gravitating body. And what this means for your descent into the black hole is that as you fall freely toward and through the event horizon, you feel weightless, genuinely and completely weightless, just as an astronaut floating in the International Space Station feels weightless even though they are quite clearly in Earth's gravitational field, because both you and everything around you are falling together, accelerating at exactly the same rate. And so there is no force pressing you against a seat, no sensation of being pulled in any particular direction, just a peaceful floating sensation as you drift along your geodesic path through curved spacetime. And this is why I say you cannot detect the horizon locally. Because there is no experiment you could perform, no measurement you could make at that precise moment of crossing, which would tell you definitively that you had just passed the point of no return. The geometry of spacetime remains smooth. Your body remains comfortable. And the only indication that something significant has happened is the mathematical fact that your future now inevitably leads deeper inward, though you have no way of knowing this through direct experience. Now I should say a few words about the particular black hole I have been describing, because the experience of crossing the horizon varies tremendously depending on the mass of the black hole in question. And I have chosen for our thought experiment the supermassive black hole at the center of our own galaxy, the one called Sagittarius A star, which has a mass of approximately 4 million times the mass of our Sun. And this is a rather important choice because it means the tidal forces you experience at the horizon are remarkably gentle, almost imperceptibly so. And let me explain what I mean by tidal forces, because this concept is essential to understanding what makes falling into a black hole potentially survivable or not. Tidal forces arise because gravity varies with distance from a massive object. So if you are falling feet first toward a gravitational source, your feet are slightly closer to the source than your head, and therefore feel a slightly stronger gravitational pull. And this difference in pull creates a stretching effect along your length, while simultaneously there is a compressive effect perpendicular to your motion because the gravitational field lines converge toward the center. And for a stellar mass black hole, one formed from the collapse of a single massive star and weighing perhaps 10 or 20 solar masses, these tidal forces become devastating well before you reach the horizon, stretching you into a long thin strand in a process which physicists rather whimsically call spaghettification. But for a supermassive black hole like Sagittarius A star, the horizon is so far from the central singularity that the tidal forces there are almost negligible. Let me give you some numbers, because I find numbers rather soothing and I hope you do too. The radius of the event horizon for a non-rotating black hole is given by the Schwarzschild radius, which is simply twice the gravitational constant times the mass divided by the speed of light squared. And for our 4 million solar mass black hole this works out to approximately 12 million kilometers, which is a substantial distance, roughly 17 times the radius of our Sun. And at this radius the tidal acceleration, the difference in gravitational pull between your head and your feet assuming you are roughly 2 meters tall, is approximately 1/1000th of the gravitational acceleration you feel standing on Earth, about 0.001 g. And this is genuinely imperceptible to human senses. You would not notice any stretching or compression whatsoever. You would simply float there feeling perfectly comfortable. And this is one of the curious paradoxes of black holes, that the most massive ones are in some sense the most hospitable to travelers, at least at the horizon, because the larger the black hole the gentler the spacetime curvature at the event horizon. And so if one were somehow compelled to fall into a black hole, one would greatly prefer a supermassive one over a stellar mass one. The crossing itself takes only a few seconds of your own proper time, the time measured by a clock falling alongside you. Because even though 12 million kilometers sounds like an enormous distance, you are falling inward at a substantial fraction of the speed of light by the time you reach the horizon. And a simple calculation suggests that passing through the immediate vicinity of the horizon, from a few hundred kilometers above to a few hundred kilometers below, takes perhaps 1 or 2 seconds by your watch. And during this brief interval you notice nothing unusual about your local environment. No flash of light, no change in temperature, no peculiar sensation, just the same peaceful, weightless floating you have experienced throughout your descent. And yet something quite remarkable is happening with respect to the outside universe. Because while only seconds pass for you, an infinite amount of time is passing for distant observers watching your fall. Though I should clarify that this statement requires some careful interpretation. What it really means is that light signals you send outward take progressively longer to climb out of the gravitational potential well and reach distant observers, asymptotically approaching infinite delay as you approach the horizon, so that from their perspective you appear to slow down and fade away, never quite reaching the horizon, while from your perspective you sail smoothly through in a matter of seconds. And this is not a paradox but simply a reflection of the fact that time passes at different rates in different reference frames, a consequence of the warping of spacetime by mass. As you cross the horizon and continue falling inward, something rather lovely happens to your view of the universe above you, because the gravitational lensing effects which have been gradually increasing throughout your descent now reach their most extreme form. And if you were to look backward, away from the black hole and toward the stars you left behind, you would see the entire visible universe compressed into a shrinking bright ring above your head, light from every direction bent so severely that it all arrives from an ever-narrowing cone of angles. And this ring grows smaller and dimmer as you fall deeper, the universe you knew retreating to a brilliant halo that eventually contracts to a single bright point and then vanishes entirely. And meanwhile, looking forward, into the black hole itself, you see only darkness, an absence of light so complete that it seems almost tangible. And this contrast between the bright ring of the receding universe and the perfect darkness ahead is one of the more striking visual features of the journey. Though I suspect you might be too preoccupied with existential considerations to fully appreciate the aesthetics. There is one more thing I should mention about the horizon before we proceed further inward, which is that it is not quite as perfectly dark and cold as classical general relativity would suggest. Because in 1974 Stephen Hawking published a remarkable paper demonstrating that when quantum mechanical effects are taken into account, black holes emit a faint thermal radiation, now called Hawking radiation, which arises from the creation of virtual particle pairs near the horizon, where the extreme curvature of spacetime can occasionally promote these fleeting quantum fluctuations into real particles, with one member of the pair escaping to infinity while the other falls into the black hole. And the net effect is that the black hole slowly loses mass and energy, radiating like a very cold black body, and the temperature of this radiation is inversely proportional to the mass of the black hole, which means that for our supermassive Sagittarius A star the temperature is extraordinarily low, approximately 15 nanokelvin, that is 15 billionths of a degree above absolute zero, and this is so cold that the radiation is essentially undetectable, emitting perhaps a few photons per year with wavelengths larger than the observable universe. And so while it is technically true that the horizon glows faintly, you would never perceive this glow. It is far too weak and far too cold, billions of times colder than the cosmic microwave background which fills all of space. And so for all practical purposes the horizon remains dark and silent, a perfect invisible threshold which you cross without ceremony or sensation. I find it rather comforting, in a strange way, that the most dramatic boundary in all of physics is also the most undetectable locally, that the point of no return is marked by no gates or guards or warning signs, that you simply drift across it in peaceful ignorance, your body undisturbed, your consciousness uninterrupted. And it is only the mathematics which tells you that something fundamental has changed, that your causal future has been irrevocably redirected, that every possible path through spacetime now leads inevitably toward the center. And perhaps this is appropriate, That the universe does not announce its most significant transitions with fanfare but allows them to happen quietly, smoothly, as natural consequences of geometry and motion. And so we find ourselves now inside the horizon, falling freely through the dark interior of the black hole, still feeling weightless, still comfortable, still alive and conscious, though our fate is now sealed in a way that it was not before, and the journey continues inward, ever inward, toward whatever awaits us at the center. But that is a subject for another section, and for now we can rest here in this curious space, inside the invisible threshold, marveling quietly at how gentle and unremarkable the crossing turned out to be. And so you have crossed the horizon, that boundary which from the outside appeared so absolute, so final, and yet from your own perspective seemed like nothing at all, just another stretch of curved space-time through which you drifted without fanfare or ceremony. You are now inside the shadow, within the region that no light can escape, and though your instruments continue to function and your thoughts continue to flow, something fundamental about the nature of space and time has changed around you, changed in a way that takes some quiet contemplation to appreciate. To understand what has happened, we must think carefully about what physicists mean when they speak of directions in space-time. In the ordinary universe you once inhabited, space and time were distinct in an important way. You could choose to move left or right, forward or backward, up or down, and all of these choices were available to you at any moment. But the direction of time was different, was it not? You could not choose to move into yesterday any more than you could choose to stop moving into tomorrow. Time carried you forward, always forward, at a rate of 1 second per second. And this forward motion was not something you could negotiate with or resist. The future simply came, whether you wished it to or not. Inside the event horizon of a black hole, something rather peculiar has occurred. The radial direction, the direction pointing toward the center of the black hole or away from it, has taken on the character that time once had. Moving toward the singularity is no longer a matter of spatial choice, no longer something you might do or not do depending on how you orient your spacecraft or fire your engines. Moving toward the singularity has become as inevitable as moving toward tomorrow. The center of the black hole lies in your future now, in a very real and mathematical sense. And just as you could never have stopped time from passing when you lived among the stars, you cannot stop yourself from approaching what lies ahead. This transformation of space into time and time into space is not mere poetry or metaphor. It emerges directly from the mathematics of general relativity, from those field equations that Einstein labored over in the second decade of the 20th century. The first solutions to those equations, describing the spacetime around a spherical, non-rotating mass, were found by Carl Schwarzschild in 1916, and for many decades these Schwarzschild solutions were the primary tool physicists used to understand black holes. But real astronomical objects rotate. Stars spin, matter swirls. Angular momentum is conserved through gravitational collapse, and so we would expect that real black holes, the ones that actually form when massive stars die or when matter accumulates at the centers of galaxies, should be spinning as well. The mathematics describing a rotating black hole proved far more challenging than Schwarzschild's original solution. And it was not until 1963 that the New Zealand mathematician Roy Kerr discovered the exact solution to Einstein's equations for a rotating mass. This Kerr solution, as it came to be known, describes what physicists believe are the most realistic black holes, the ones that spin on an axis just as the Earth spins or the Sun spins. carrying their angular momentum with them even as they collapse to extraordinary densities. The black hole at the center of our own galaxy, that quiet giant known as Sagittarius A*, is almost certainly a Kerr black hole, spinning at some substantial fraction of the maximum possible rate. The difference between a Schwarzschild black hole and a Kerr black hole becomes most apparent in the nature of the singularity itself. In the Schwarzschild solution, describing a perfectly spherical and non-rotating black hole, the singularity is a point. Or rather, it is not quite accurate to call it a point in space, because as we have discussed, spatial directions have a different meaning inside the horizon. The Schwarzschild singularity is better understood as a moment in time, a final moment toward which all infalling trajectories converge. A moment when the mathematics predicts that density becomes infinite and the curvature of spacetime becomes infinite, and our equations, elegant as they are, simply break down and can tell us nothing more. But the Kerr solution presents a different geometry altogether. The rotation of the black hole smears the singularity, if you will, into a ring rather than a point. This ring singularity lies in the equatorial plane of the rotating black hole, perpendicular to its axis of spin, and it has some rather unusual properties that occupied theoretical physicists for many years after Kerr's discovery. The mathematics seems to suggest, and here we must be very careful to distinguish between what the equations say and what nature actually permits, that the ring singularity might be approached from certain directions without necessarily being struck. There were even speculative papers in the 1960s and 1970s wondering whether an infalling observer might pass through the ring, through the center of that mathematical circle, and emerge into some other region of spacetime entirely. These speculations led to the development of visual tools for understanding the causal structure of black holes, and among the most important of these tools is the Penrose diagram, named after the British mathematical physicist Roger Penrose, who developed them during the 1960s. A Penrose diagram is a particular way of drawing spacetime that preserves the paths that light rays can follow, the causal connections between events, while compressing infinite distances into a finite picture that can be drawn on a page or contemplated in the mind. In a Penrose diagram of a Schwarzschild black hole, you can see quite clearly how the singularity lies in the future of any observer who crosses the horizon, how there is no path, no sequence of events that could lead from inside the horizon back to the outside universe. The diagram makes visible what the equations already told us, that the interior of a black hole is a region from which the only possible future leads deeper inward. The Kerr solution, when drawn as a Penrose diagram, reveals additional structure that the Schwarzschild solution does not possess. Inside the outer event horizon of a rotating black hole, there exists what physicists call an inner horizon, sometimes referred to as the Cauchy horizon after the French mathematician Augustin-Louis Cauchy, who made foundational contributions to the theory of differential equations. The Cauchy horizon marks a boundary where the predictability of physics, the ability to calculate what will happen next from what has happened before, may break down entirely. Beyond the Cauchy horizon, the equations suggest that signals from your own past could catch up to you, that causality itself might become tangled in ways that would allow effects to precede their causes or information to loop back upon itself in paradoxical circles. Whether the Cauchy horizon actually exists in real astrophysical black holes, or whether quantum effects or the accumulation of infalling matter and radiation would destabilize it, remains an open question. The mathematics is elegant and consistent, but mathematics describes what is possible according to a given set of equations, And nature is not obligated to realize every mathematical possibility. What we can say with some confidence is that the interior structure of a rotating black hole is more complex, more rich in its geometry, than the simple spherical collapse that Schwarzschild first described. The possibility of gravitational collapse leading to these extreme states of matter was explored theoretically long before any observational evidence for black holes existed. In 1939, J. Robert Oppenheimer, who would later become famous for quite different reasons, collaborated with his student Hartland Snyder on a paper calculating what would happen to a star that exhausted its nuclear fuel and collapsed under its own gravity. Their paper, published in Physical Review, showed that from the perspective of an outside observer, the collapsing star would appear to slow down as it approached its gravitational radius, that final flicker of light taking infinitely long to reach distant telescopes. But from the perspective of the star itself, of someone riding along with the collapsing matter, the collapse would proceed smoothly through the horizon and beyond, a result that seemed so strange to physicists of that era that many doubted whether such objects could really exist. Let us return now to your own experience, to your descent through this interior region that Schwarzschild first mapped mathematically and that Kerr refined for rotating masses. If you have fallen into a supermassive black hole, one containing millions or billions of times the mass of our Sun, the tidal forces near the horizon are gentle, as we discussed earlier, and they remain gentle for some time as you fall inward. This means that you have subjective time, minutes, or even hours of conscious experience within the interior of the black hole before the final approach to the singularity begins to make itself felt. For a black hole the size of Sagittarius A*, which contains roughly 4 million solar masses within its event horizon, calculations suggest that you would have approximately 20 minutes of proper time, of experience duration, between crossing the horizon and approaching the region where the singularity lies. 20 minutes is not a long time by the standards of a human life, but it is not negligible either. It is long enough to think, to remember, to contemplate what has happened and what is to come. It is long enough to watch the strange geometry around you evolve and shift as you fall ever deeper into the gravitational well. And what would you see, looking around you during these final minutes? The answer depends on what else has fallen into the black hole alongside you. If you were alone, a solitary observer in an otherwise empty void, you would see mostly darkness ahead of you, the darkness toward which space itself seems to funnel and flow. The radial direction, remember, has become time-like, and so when you look toward the singularity, you are in a sense looking toward the future, looking toward a destination you cannot avoid but which does not present itself to your eyes in any ordinary way. Looking sideways, however, looking in directions perpendicular to your fall, you might see other things. If there were other objects falling into the black hole, other spacecraft or other observers or simply chunks of matter that had crossed the horizon before or after you, these objects would be visible to you, their light still able to reach your eyes. But here is the subtle strangeness of the interior geometry. These other objects, even if they seem close to you, even if you could reach out and nearly touch them, are separated from you by uncrossable time. The geodesics of space-time, the paths along which objects freely fall, diverge and separate inside the horizon in ways that make rendezvous impossible. Two observers who cross the horizon at the same moment but at slightly different locations cannot, in general, bring themselves back together. They are like ships passing in the night, able to signal each other with lamps and flags, able to see each other quite clearly, but carried by currents that no amount of rowing can overcome. This separation by time rather than space gives the interior of the black hole a peculiar loneliness. Everything that falls in shares the same ultimate fate, the same approach toward the singularity or the ring singularity or whatever lies at the deepest center. And yet each infalling object experiences this fate in its own private bubble of space-time, surrounded by companions it cannot reach, visible to observers who cannot intervene. The mathematics describes this beautifully. The Penrose diagrams show it clearly, but the experience itself would be something no human has ever known, a falling that cannot be stopped, surrounded by others who are also falling and who can only wave as they pass. The light from the outside universe, the light that entered the black hole at the same time you did or shortly afterward, still reaches your eyes during this descent. You can still see the stars, though they are gathered now into a shrinking ring behind you, concentrated into a halo of light that circles your field of vision. This light is blue-shifted, energized by falling into the gravitational well alongside you, but it is real light from real stars, a final connection to the universe you have left behind. As you fall deeper, this ring of light grows smaller and more intense, the outside universe compressing into a bright circle that shrinks toward a point as the singularity approaches. There is something almost gentle about this gradual farewell, this slow dimming of all that was once your home. As you continue your descent, there comes a point where the journey begins to change in character, not suddenly, not with any violence or alarm, but with a gradual shift in the way space itself treats different parts of your body. This phenomenon has a rather whimsical name, one that belies the profound physics underlying it, and that name is spaghettification. The term was introduced to popular science by Stephen Hawking in his 1988 book A Brief History of Time, where he chose this playful word to describe something that had long been understood in the mathematics of general relativity but had never quite found its way into everyday language. Hawking had a gift for making the cosmos accessible, for taking equations that would fill chalkboards and distilling them into images that anyone could hold in their mind. And spaghettification is perhaps one of his most memorable contributions to our vocabulary. It refers to the stretching of objects into long, thin shapes, like strands of pasta, under the influence of extreme tidal forces. And while the name might make you smile, the physics behind it is as elegant and inevitable as anything in nature. To understand why this stretching occurs, we must return to a concept that you encounter every day without perhaps realizing it, and that is the concept of tidal forces. Here on Earth, the ocean tides are caused by the Moon's gravity pulling slightly more strongly on the side of our planet closest to it than on the side farther away. This difference in gravitational pull across an extended body is what we call a tidal force, and it is not unique to the Earth-Moon system. It occurs wherever gravity varies from one point to another, and near a black hole, this variation becomes extraordinarily pronounced. The mathematics tells us that tidal forces scale with the mass of the gravitating object divided by the radius cubed, which means that getting closer to the source of gravity increases the tidal force very rapidly indeed. Halving your distance from a black hole does not merely double the tidal force, it increases it eightfold. And this cubic relationship is why the effects become so dramatic as you approach. For stellar mass black holes, those formed from the collapse of massive stars at the end of their lives, the consequences of this scaling are quite significant. Consider a black hole like Cygnus X1, which has been studied extensively since its discovery in the early 1970s and is estimated to contain roughly 20 times the mass of our Sun. This is an enormous amount of matter by any human standard. yet it is compressed into a region so small that its event horizon is only about 60 kilometers across. Because the mass is concentrated into such a compact space, the tidal forces become extreme while you are still quite far from the horizon. In fact, for a black hole of this size, the stretching would begin to become noticeable and then uncomfortable and then rather more than uncomfortable while you were still thousands of kilometers away from the point of no return. The spaghettification, in this case, occurs well outside the event horizon, in a region of space from which light can still escape and from which, in principle, you could still turn back, though of course by the time you felt the stretching begin, the time for turning back would already be growing very short. The situation is quite different for supermassive black holes, those giants that sit at the centers of galaxies and contain millions or even billions of solar masses. These objects are so massive that their event horizons are correspondingly huge, stretching across millions of kilometers, distances comparable to the orbits of planets around ordinary stars. Because the radius is so large, and because tidal forces scale with mass divided by radius cubed, the tidal forces at the event horizon of a supermassive black hole are actually quite gentle. You could cross the horizon of a sufficiently large black hole and notice nothing unusual at all. No stretching, no discomfort, just the quiet continuation of your fall. The spaghettification would come later, much later, as you continued your descent toward the singularity at the center, and only then, deep within the black hole's interior, would the tidal forces grow strong enough to begin the stretching in earnest. This is one of the counterintuitive truths of black hole physics, that the largest black holes are in some ways the gentlest, at least at first, while their smaller cousins are more immediately perilous. Astronomers have actually observed what happens when objects venture too close to black holes and experience these extreme tidal forces, though the objects in question are not people or spacecraft but stars, entire suns torn apart by gravity. These events are called tidal disruption events, and they produce brilliant flares of radiation that can be seen across the universe. One particularly well-studied example is designated PS1-10JH, which was observed in 2010 by the Pan-STARRS Survey telescope in Hawaii. In this event, a star wandered too close to a supermassive black hole at the center of a distant galaxy, and the tidal forces overwhelmed the star's own gravity, which normally holds it together in a spherical shape. The star was stretched and torn, its material drawn out into a long stream that spiraled around the black hole and gradually fell inward, heating up and glowing brightly as it did so. The flare was visible for months, a slow, bright announcement that somewhere in the cosmos, a star had met its end not in a supernova explosion but in a more intimate encounter with extreme gravity. These observations confirm what the mathematics predicts, that tidal forces near black holes are real and powerful and capable of destroying even objects as large and as tightly bound as stars. But let us return to your own experience, to the gentle falling that you are undertaking, and consider what the stretching would actually feel like as it begins. The key word here is gradual. There is no sudden snap, no violent wrenching, just a slow awareness that the pull of gravity on your feet, which are closer to the black hole, is slightly stronger than the pull on your head, which is slightly farther away. This difference in pull creates a tension along the length of your body, a stretching sensation that might at first feel like being gently elongated, as if you were made of soft taffy being slowly drawn out. At the same time, the tidal forces would create a lateral compression, squeezing you inward from the sides, because the gravitational field lines are converging toward the center of the black hole. You would become thinner as well as longer, your body slowly reshaped by the geometry of space-time itself. At relatively modest tidal forces, this sensation might be almost pleasant, a kind of cosmic massage, a feeling of being gently pulled and pressed by invisible hands. If the tidal force across your body were equivalent to about 1 Earth gravity, you would feel effectively weightless, floating as astronauts do in orbit, but with an added sensation of very slow elongation. Your arms would drift upward slightly, your spine would lengthen, and you might feel a mild ache in your joints as the cartilage was allowed to expand in ways it normally cannot. This is not dissimilar to what happens to astronauts on the International Space Station, who often grow a few centimeters taller during their time in microgravity, though of course the stretching in a black hole would eventually go much further than that. The experience would be strange, certainly, and unfamiliar, but not painful at first, more like floating in a warm current that is slowly, inexorably, drawing you along. The word inexorable is important here. Nothing you could do would stop the stretching once it began. No amount of resistance, no clever maneuver, no last-minute escape plan. The tidal forces are a feature of space-time itself, and space-time does not negotiate. But this inevitability carries with it a certain peace, a release from the burden of trying to change what cannot be changed. You are simply a part of the physics now, a small piece of matter following the curves of space-time exactly as the mathematics says you must. There is no violence in this, only geometry, only the quiet unfolding of laws that have held true since the universe began. It was these very laws, the predictions of general relativity regarding black holes and their behavior, that were spectacularly confirmed on September 14, 2015, when the twin detectors of the Laser Interferometer Gravitational Wave Observatory, known as LIGO, recorded a signal that would change our understanding of the cosmos. The signal was designated GW150914, and it was caused by the merger of two black holes roughly 1.3 billion light-years away, one containing about 36 solar masses and the other about 29. These two massive objects had been spiraling around each other for eons, losing energy to gravitational waves, ripples in the fabric of space-time that spread outward at the speed of light. As they drew closer and closer, their orbital dance accelerated, and in the final fraction of a second, they merged into a single black hole of about 62 solar masses, with the remaining 3 solar masses converted entirely into gravitational wave energy. The signal that LIGO recorded lasted only about 0.2 of a second, a chirp that rose in frequency as the black holes spiraled together and then cut off abruptly as they merged. And yet that brief whisper contained within it a confirmation of everything Einstein had predicted a century earlier. The detection of GW150914 was the first direct observation of gravitational waves and the first direct evidence that black holes exist exactly as general relativity describes them, not merely as theoretical curiosities but as real objects that merge and interact and shake the very fabric of space-time. The scientists who made this detection had spent decades building instruments of almost unimaginable sensitivity, capable of measuring changes in length smaller than 1/10,000th the diameter of a proton, and their patience and precision were rewarded with a signal that matched the theoretical predictions with extraordinary accuracy. The black holes that merged in GW150914 had event horizons. They had the masses and spins that general relativity predicted, and they behaved during their final moments exactly as Einstein's equations said they must. This confirmation gives us confidence that our understanding of black holes is correct, that the spaghettification and the stretching and the gentle falling are real physical processes. Not merely thought experiments but actual experiences that matter near black holes must undergo. And so, as you continue your descent, you can rest assured that the physics carrying you inward is well understood, tested and confirmed by observations across the electromagnetic spectrum and now in gravitational waves as well. The stretching that you feel is the same process that tears apart stars in tidal disruption events, the same process that would occur near the black holes whose merger LIGO detected, the same process predicted by equations written down a century ago by a patent clerk in Switzerland who had the audacity to reimagine space and time. There is comfort in this continuity, in knowing that you are not experiencing something unknown but rather something deeply understood, a natural consequence of mass and gravity and the geometry of the universe. The stretching continues, gradual and unceasing, and you are becoming longer and thinner, your outline beginning to blur as the tidal forces reshape you. But there is no hurry here, no rush toward any conclusion, only the slow and steady application of forces that have been at work since the black hole first formed. Time passes, though the meaning of time is becoming strange now, and you are simply falling, elongating, following the curves of space-time toward whatever lies below. The physics is impeccable, the experience is serene, and the gentle stretching carries you ever onward, deeper into the embrace of gravity, further from everything you once knew, and closer to the mysteries that still wait to be understood. And so we arrive at a place where our mathematics begins to whisper rather than speak, where the equations that have guided us so faithfully through the warped geometry of space-time start to falter and blur like words written on paper that is slowly dissolving in water. This is not a failure of human cleverness, not a limitation we might overcome with better instruments or more powerful computers, but rather something more profound and, in its own quiet way, more beautiful. General relativity, that magnificent framework Einstein gave us more than a century ago, makes a rather extraordinary confession when we follow its predictions inward toward the heart of a black hole, because it tells us with perfect mathematical clarity that a singularity must exist there, a point of infinite density where all the infalling matter has been compressed beyond compression. And yet in making this prediction, the theory also acknowledges that it cannot possibly be correct about what happens in such a place, that it is describing something beyond its own jurisdiction, like a map that marks a region with the honest notation that says here the cartographer's knowledge ends. This is what physicists sometimes call the theory predicting its own breakdown, and there is something gently humble about it. Something almost poetic in the way our best description of gravity and space-time bows its head at the threshold of the extreme and admits that a deeper understanding must eventually take over. The singularity that general relativity predicts is not so much a place as an absence of place, not so much a moment as an ending of moments. And while the mathematics can trace curves of infalling matter right up to this boundary of knowledge, it cannot cross over and tell us what lies within. We are left at the edge of a mystery, and that edge is smaller than you might imagine, smaller than anything you have ever encountered in your daily experience of the world. To understand just how small we must go before our current physics loses its footing, we turn to what are called the Planck scales, named after Max Planck, who first identified these fundamental units in the early 20th century. The Planck length is approximately 1.6 times 10 to the negative 35 meters, a number so small that writing it out in full would require placing a decimal point and then 34 zeros before arriving at the digit 1 and the digit 6. To offer some sense of this, consider that a single proton, already so tiny that billions of them could fit across the period at the end of a printed sentence, is still roughly 100 billion times larger than the Planck length. If you were to shrink down by the same factor that separates your current size from a proton, you would still be nowhere close to the Planck scale, not even within many orders of magnitude. This is the length at which the smooth fabric of space-time, the continuous curved surface that general relativity describes so elegantly, may itself become grainy and discrete, where quantum effects in gravity can no longer be ignored, where the very notion of distance as we understand it may cease to have meaning. There is also a Planck time, approximately 5.4 times 10 to the negative 44 seconds, the time it would take light to travel one Planck length. This is not merely a short duration but a threshold below which our usual concept of time flowing smoothly from moment to moment may break down entirely, where causality itself becomes uncertain, where the difference between before and after might blur into something our minds have no experience of and no words for. When physicists speak of what happens at a singularity, when they wonder what replaces the infinite density that general relativity predicts, they are asking questions about physics at or below these Planck scales, questions that require theory we do not yet possess, a theory that would marry the quantum mechanical description of the very small with the gravitational description of the very massive, a union that has so far eluded our most persistent efforts. And yet there are candidates, tentative frameworks that physicists have been carefully constructing, theories that reach toward this regime with mathematical tools that might, when refined and tested, illuminate what general relativity cannot. One such approach is called loop quantum gravity, developed beginning in the 1980s and continuing to the present day through the work of physicists including Abhay Ashdekar, Carlo Rovelli, and Lee Smolin, among many others. Loop quantum gravity proposes something rather remarkable about the nature of space itself, suggesting that what appears to us as smooth and continuous is actually, at the Planck scale, woven from discrete units, tiny loops of gravitational field that link together like the finest possible chainmail, creating the fabric we experience as the space through which we move and in which we live. In this picture, there is a smallest possible chunk of volume, a minimum quantum of space below which further division makes no sense, below which the question of smaller simply has no answer. The consequences of this proposal for black holes are profound and gently reassuring. Because if space cannot be compressed below a certain quantum minimum, then true singularities cannot form. Rather than collapsing to a point of infinite density, matter falling into a black hole would reach a state of maximum but finite compression, a quantum bounce that might, in some versions of these calculations, lead to a slow expansion out the other side, perhaps into a new region of spacetime, perhaps through processes that take longer than the current age of the universe to complete. The crushing inevitability of the singularity softens in this picture, replaced by something strange but finite, something that quantum mechanics prevents from reaching the mathematical infinity that general relativity predicts. This remains theoretical, unconfirmed by experiment, existing only in equations and computer simulations, but it offers a glimpse of how our understanding might eventually grow to encompass even these most extreme places. Another approach comes from string theory, that vast and intricate framework which proposes that the fundamental constituents of reality are not point-like particles but tiny vibrating strings of energy, so small that they too exist at or near the Planck scale. Within string theory, a rather startling picture of black holes has emerged, developed significantly by the physicist Samir Mather in the early 2000s and sometimes called the fuzzball hypothesis. In this picture, a black hole has no interior at all in the classical sense. No empty space stretching down toward a central singularity, but is instead entirely filled with a tangled, complicated configuration of strings and higher dimensional objects called brands. The event horizon itself becomes not a mere mathematical boundary but an actual physical surface, a place where the fuzzball ends and the external universe begins. Infalling matter would not pass through into an interior void but would instead be absorbed into this stringy structure, spreading out across it like warmth diffusing through a fabric. What you would experience in such a scenario is difficult to say, beyond the reach of our current ability to translate these mathematical ideas into sensory predictions. But it differs dramatically from the classical picture and eliminates the singularity by eliminating the interior space in which it would have formed. There is also a profound idea that has emerged from string theory and related investigations, known as the holographic principle, which received its most precise formulation in 1997 when the physicist Juan Maldacena demonstrated a remarkable correspondence between two apparently very different theories. What Maldacena showed, in what is called the AD-CFT correspondence, is that a gravitational theory in a curved spacetime can be exactly equivalent to a quantum field theory without gravity living on the boundary of that spacetime, like a hologram in which all the three-dimensional information of an image is encoded on a two-dimensional surface. Applied to black holes, this suggests something extraordinary, that all the information about everything that has ever fallen through an event horizon, every book and memory and configuration of matter, might be encoded not in a singular point at the center or spread through some interior volume, but rather on the horizon itself, written in a language of quantum degrees of freedom on that two-dimensional surface. This connects to one of the deepest puzzles in modern physics, the black hole information paradox, first clearly articulated by Stephen Hawking in 1976. Hawking had shown that black holes emit radiation, that they slowly evaporate over vast timescales. But the radiation he calculated seemed to carry no information about what had fallen in, to be perfectly random and featureless regardless of whether the black hole had formed from a collapsing star or a collection of grand pianos or a library of every book ever written. If this were true, then when a black hole finally evaporated completely, all that information would be lost forever, destroyed in a way that violates one of the fundamental principles of quantum mechanics, which insists that information is always conserved, always recoverable in principle even when scrambled beyond any practical hope of retrieval. This paradox has driven decades of research, generating more papers than almost any other question in theoretical physics, precisely because it sits at the intersection of quantum mechanics and gravity, precisely because resolving it might teach us something essential about how these two frameworks fit together. Recent work has offered tantalizing hints that information might escape after all, that Hawking's original calculation, while essentially correct in its regime, missed subtle quantum effects that become important over the full lifetime of an evaporating black hole. In 2019 and the years following, calculations involving what are called quantum extremal surfaces suggested that the radiation a black hole emits does eventually begin to carry information about the interior, that the entropy of the radiation, after initially growing as Hawking predicted, eventually begins to decrease in exactly the way it would need to if information were being transferred out. These calculations are technical and rely on simplifying assumptions, working in toy models rather than realistic four-dimensional black holes, but they represent genuine progress on a problem that once seemed utterly intractable, gentle hints that the universe may conserve information as quantum mechanics demands, that nothing is truly lost even behind an event horizon. What does this mean for you? for your imagined journey into a black hole, for the question of what you would actually experience in your final moments. The honest answer is that we do not know, that the destination of your fall remains beyond our current understanding, that the singularity you approach may not be a singularity at all, that the interior you traverse may not be an interior, that the information that constitutes you may persist in ways we cannot yet describe. This is not a frustrating gap in our knowledge, but rather an invitation, an open question that may take generations more to answer, a mystery that physicists are gently working to illuminate with whatever mathematical candles they can kindle. The theories we have discussed, loop quantum gravity and string theory and holography, are not yet confirmed, not yet tested against experiment, existing in that liminal space between speculation and established fact where much of theoretical physics necessarily lives when it ventures toward the extreme. And perhaps there is something restful in that uncertainty, something that invites sleep rather than anxious waking, the recognition that the universe still holds mysteries we have not solved, that the very fabric of space and time at its most fundamental level remains beyond our complete comprehension. What you would experience at the heart of a black hole is a question for future physicists, future theories, future instruments we have not yet imagined, and in the meantime, we are left with our best current understanding, which takes us so close to the answer, through the event horizon and down into the tidal embrace of curvature, but stops short at the Planck scale, at the edge of where physics dreams of deeper truths it has not yet awakened to see. And now, if you will, let us drift slowly back from the singular point at which we arrived, and allow our perspective to widen once more, like a camera pulling away from a single candle flame to reveal the vast dark room in which it flickers, and then further still, through the walls, above the roof, into the night sky, past the moon, beyond the planets, outward and outward until the entire Milky Way becomes a pale smear of light no larger than a thumbprint held at arm's length, and then further still, until even that thumbprint shrinks to a single point among countless other points, each one a galaxy, each galaxy containing hundreds of billions of stars, and among those stars, scattered like seeds fallen between the rows of a cosmic garden, lie the black holes, more of them than you might ever have imagined, silent and patient and everywhere. In the year 2022, a team of researchers led by Alex Cecilia and colleagues at the International School for Advanced Studies in Trieste published a careful accounting, a kind of cosmic census, in which they attempted to estimate just how many stellar mass black holes exist within the observable universe, and after considerable calculation involving the rates at which stars are born and the rates at which massive stars collapse at the ends of their lives, they arrived at a number so large that it almost loses meaning when spoken aloud, and yet we shall speak it anyway, gently and without fanfare, and that number is approximately 40 quintillion, which is to say 40 billion, or if you prefer to see it written out, a 4 followed by 19 zeros, and each of these black holes was once a star, and each of these stars burned for millions or billions of years before its fuel was exhausted, and each collapse was a kind of transformation, a folding inward, a departure from the visible universe into a state of permanent hiddenness, and now they drift through the cosmos in numbers beyond counting, most of them entirely undetected, their presence known only through the subtle gravitational tugs they exert on passing matter or through the rare and fortunate circumstance of a companion star from which they might draw material and thereby reveal themselves in the glow of an accretion disk. 40 quintillion is a number that resists easy comprehension, and so perhaps it helps to consider that for every grain of sand on every beach on Earth, there are roughly 10,000 stellar mass black holes somewhere in the observable universe, each each one a collapsed remnant of a star that once shone, each one now perfectly dark, perfectly silent, perfectly patient. And this is only counting the stellar mass variety, the black holes born from the deaths of massive stars, which typically range from a few times the mass of our Sun up to perhaps 50 or 100 solar masses. And yet there are other black holes, far larger, lurking at the centers of galaxies, grown fat over billions of years through the consumption of stars and gas and the mergers of smaller black holes. And these are the supermassive black holes. And their masses are truly staggering. Consider, for instance, the object known as DN618, which resides at the heart of a quasar some 10 billion light-years from Earth. And current estimates suggest that this black hole contains approximately 66 billion times the mass of our Sun, which means that if you could somehow gather together 66 billion stars identical to our own and compress them all into a single point, you would have something approaching the mass of DN618. And its event horizon spans a diameter roughly 11 times larger than the entire orbit of Neptune, which is to say that our entire solar system, from the Sun out past the orbits of all the planets, could fit comfortably within the event horizon of this single black hole with room to spare. And yet even DN618 is not the largest black hole known to us. That distinction belongs, at least for the moment, to a truly colossal object known as Phoenix A, which sits at the center of a galaxy cluster called the Phoenix Cluster, approximately 5.8 billion light-years away. And Phoenix A is estimated to contain 100 billion solar masses, making it perhaps the most massive black hole ever measured. Though such measurements carry considerable uncertainty, and there may well be others of similar or greater size waiting to be discovered in distant galaxies we have not yet examined closely enough. And when you try to picture 100 billion solar masses gathered into a single black hole, the imagination simply fails, because there is nothing in ordinary experience that prepares you for such a scale. And yet there it is, real and present, bending space-time so severely that its event horizon likely spans hundreds of billions of kilometers, a dark sphere larger than some small galaxies, patient and quiet and utterly black. And between the stellar mass black holes and the supermassive black holes, there exists a spectrum of intermediate cases, some of them still poorly understood. Black holes of thousands or tens of thousands of solar masses that may represent seeds from which the supermassive black holes eventually grew, or which may have formed through the direct collapse of primordial gas clouds in the early universe. And the census is still being taken, the catalogue still being assembled, and every year new detections are made through gravitational wave observatories like LIGO and Virgo, which can feel the ripples in space-time produced when two black holes spiral together and merge. And each such detection adds another entry to the cosmic ledger, another confirmation that black holes are not rare curiosities but rather a fundamental and ubiquitous feature of the universe. In fact, when you add up all the mass contained within black holes throughout the observable universe, both the stellar mass variety and the supermassive behemoths at galactic centers, you arrive at a rather remarkable conclusion, which is that black holes may contain approximately 1% of all baryonic matter in the universe, and baryonic matter is simply the ordinary matter made of protons and neutrons, the stuff of which stars and planets and people are made. And so 1% may not sound like very much. But when you consider the vastness of the universe and the sheer quantity of matter it contains, 1% becomes an enormous sum, a significant fraction of everything that exists in visible form, now locked away behind event horizons, removed from the ordinary processes of the cosmos, participating in the universe's evolution only through gravity and through the slow patient accumulation of additional mass. And here we might pause to consider a curious fact about black holes that was first articulated by the physicist Jacob Bekenstein in 1972, which is that a black hole carries entropy. And entropy, in the language of physics, is a measure of disorder, or more precisely, a measure of the number of different microscopic arrangements that could produce the same macroscopic state. And Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon rather than to its volume, which was a deeply surprising result, because for ordinary objects, entropy scales with volume, and yet for black holes, it scales with surface area. And this led to profound implications for our understanding of information and the nature of physical reality. And when you calculate the actual entropy of a typical black hole, you find that it is astonishingly large, far larger than the entropy of any other object of comparable size. To put this in perspective, consider that a black hole with the mass of the Sun would carry more entropy than all the stars in the observable universe combined. And this suggests that black holes are not simple objects at all, but rather objects of unimaginable internal complexity, containing more possible configurations, more hidden information, than anything else of their size could possibly contain, and what this information represents, and how it is encoded, and whether it might ever be retrieved. These are questions that continue to occupy theoretical physicists today, decades after Bekenstein first made his observations, and the answers remain elusive. But the implication is clear, that when matter falls into a black hole, it does not simply vanish, but rather becomes part of this vast reservoir of hidden complexity, encoded in ways we do not yet understand, preserved in some form that the laws of physics seem to demand. And yet even black holes, as patient and permanent as they seem, will not last forever, because in 1974, Stephen Hawking made a remarkable theoretical discovery, which is that black holes emit radiation, a faint thermal glow that arises from quantum mechanical effects near the event horizon. And this radiation, now known as Hawking radiation, carries energy away from the black hole, and because energy and mass are equivalent according to Einstein's famous relation, this means that black holes very slowly lose mass over time, shrinking imperceptibly with each passing moment, and given enough time, an unimaginably long span of time, a black hole will evaporate entirely, radiating away all of its mass until nothing remains. For a black hole with the mass of our Sun, this evaporation process would take approximately 10 to the power of 67 years, which is a number so large that it defies any intuitive grasp, because the current age of the universe is only about 14 billion years, or roughly 10 to the power of 10 years. And so the evaporation time for a solar mass black hole is not merely longer than the age of the universe, but longer by a factor of 10 to the power of 57, which is to say that if you wrote out the age of the universe in years and then multiplied it by a number with 57 zeros, you would still not reach the time required for a solar mass black hole to evaporate. And for larger black holes, the supermassive giants at galactic centers, the evaporation time is longer still, scaling as the cube of the mass, so that a black hole like Phoenix A would persist for durations that make even 10 to the 67th years seem brief by comparison. And this means that black holes will be among the last macroscopic structures to exist in the universe, outlasting the stars by an incomprehensible margin, because the stars will all burn out within the next 100 trillion years or so, and the galaxies will disperse, and the atoms themselves will eventually decay if certain theories of physics are correct, and the universe will grow cold and dark and empty in a state sometimes called the heat death, when all useful energy has been exhausted and nothing remains but a thin haze of particles drifting through infinite darkness. And yet even in this final epoch, the black holes will persist, slowly evaporating but still present, the last islands of gravitational structure in a cosmos that has otherwise dissolved into thermal equilibrium. And they will continue to persist for timescales so vast that the entire preceding history of the universe, from the Big Bang through the formation of galaxies and stars and planets and life, will seem like the first fraction of the first second of the first day of an endless calendar. And so if you were to fall into a black hole, if you were to cross that event horizon and leave the visible universe behind, you would become part of one of these most patient, most enduring structures, your matter and your information joining the vast hidden complexity within, encoded in ways that physics does not yet fully comprehend, and you would drift with the black hole through the remaining ages of cosmic history, through the death of the last stars and the slow cooling of the universe, through timescales so long that numbers fail to convey their meaning, and the black hole would carry you, or what remains of you, what information once described you, through the quiet dark between the stars, part of the universe's deepest architecture, a piece of the cosmic inventory that will persist when all else has faded, patient and silent and present, drifting among the infinite dark.